kind invitation. I'm Sridharan Devarajan. I'm an associate professor at the Center for Neuroscience and associate faculty at the Computer Science and Automation Department at Indian Institute of Science, Bangalore. Today, I thought I'd share with you some of our recent work on efficient remedies for outlier detection with a kind of generative model called variational autoencoders. So I would like to mention that, given that this is an online talk, it's going to be tricky for me to see who has questions. For example, if you raise your hand or something like that, I won't be able to see that. So, my request is if you have any questions, please feel free to unmute yourself and ask, because the topic requires a fair bit of background. I'm going to try to cover it at as high a level as possible, so that most people can understand the sort of the central message of this talk. But there are bound to be questions because there's a lot of fairly in-depth material here. So please feel free to unmute yourself and ask. Again, it's more important that I convey what the sort of the central idea of what I came out to convey, rather than going through all my slides. Right? That is less of a priority for me at this stage. Yeah. Okay. So this research was done in collaboration with many wonderful collaborators at Google Research. Kushal Chauhan, the student author, Dr. Pradeep Shenoy, and Dr. Manish Gupta. And we have a couple of articles, a workshop paper and a conference paper submitted based on this. So I can also give you the links of that work if you're interested. Okay, so let's start with some of the terms in the title, right? It started by saying outlier detection, right? Efficient remedies for outlier detection. What is outlier detection, right? And why do we need outlier detection? So occasionally, because again, I can't see, obviously, unlike an offline talk, I can't see you all directly. I will do a spot check of the mic, right? So to make sure that we're all connected and you're all hearing me. So let me do that spot check right away. Are you all able to hear me? Is everything clear?
Yes, yes.
Okay, great. I need that yes, right? Because what will happen otherwise is I will keep on presenting. Maybe my internet connection gets disconnected. I'll keep on presenting without even realizing it, right? So I may be presenting for 10 minutes without realizing that I got disconnected. So I'll do this spot check frequently. So request one of you to quickly tell me if if you're able to hear me. Just a quick yes will help. Yeah. Okay.
Sure,
so what is outlier detection and why do we need? Yeah. Thank you. So what is outlier detection and why do we need outlier detection, right? So many of you may have heard of deep learning models throughout this workshop. Many speakers would have spoken about these types of more novel models, right? Now, one thing we know is that deep learning models are here to stay, right? There are many, many real world applications where deep learning models are being used. They are even sometimes employed in critical safety related applications, including driving, including things like medical diagnoses and things like this, right? But one of the dangerous things with deep learning models is that they can make very confident predictions even when they're making mistakes, right? So here's a very famous classic example. So this particular deep learning model labeled this image as a panda. You obviously, all of you all recognize that. It's about 60% confidence, right? Then with a little bit of perturbation to the image, it's now calling this a gibbon, right? A type of monkey with almost 100% confidence, right? So it's making a very mistaken classification, but with a lot of confidence. And this typically happens, these types of errors happen when the test data, that is this type of image that you present to the model, is far removed from the training data. That is, the data that was used to train the model is what the model is familiar with, right? So, but when you present something that is either deliberately somehow corrupted, like in this case, like in this adversarial example case, or due to other reasons is very different from the kind of training data that the model saw, then the model can make incorrect predictions and oftentimes very confident and incorrect predictions, right? Now, so we need this type of model confidence in many real world applications, like for medical imaging and so on. If you're trying to diagnose, a doctor is trying to diagnose some kind of pathology from brain scans, for example, and the model says something about, whether the person has a tumor or not. Um, the model should not make an incorrect diagnosis confidently, right? Uh, Both missing a tumor when it's really there or falsely flagging a tumor when it's not there have serious consequences. And if the model is not confident about that prediction, it should say that very clearly, right? So I'm making a classification, I'm making a judgment, but I'm not confident about it, right? So then the doctor can step in and sort of take over and try to address this, look at the images and try to make a decision there. Right? So accurate model confidence is an important thing, right? Not just model accuracy, but also model confidence. Now, there are a few different ways that one can train deep learning models to tell us reliable measures of their confidence. Right? And I've just illustrated, I've just mentioned two different ways here. One is this ConfidNet, for example, where you have a conventional convolutional network. You present the network with an image. There's a classifier that classifies it into one of k labels, and it's going to tell you, oh, this is an elk, a moose, a deer, whatever it is, right? So it's going to give you some classification label to it. But in addition to the conventional classification label, this model also has an add-on component, this particular module called the ConfidNet, which also predicts what is the model's confidence with making that decision, right? And what this particular paper does is it trains the model's confidence to be in line with its prediction accuracy. That is, if the model is going to be fairly accurate, right? It knows for sure, right? It knows that this is what the object is. It's going to have high confidence in that rating. But if it's a little bit unsure what that object is, it's going to give a low confidence in the rating, right? If it's going to be inaccurate decisions are accompanied by low confidence. Accurate decisions are accompanied by high confidence. So this type of added modules and so on, can be done. There's also other very popular methods like temperature scaling and so on, which have been used in literature that basically tweak your output function here, right? In order to make it look more reflective of the model's accuracy, right? The confidence goes in line with model accuracy. This general field of work is called model calibration. And these types of solutions work for supervised models, right? Models where you have data labels available and you can train the model to give some kind of confidence in its classification accuracy, its classification label. So, but this is not the type of model that we're going to see in this talk. We are going to be looking at unsupervised models. So models that learn from label-free data. So what do we want from these models? We want to get an estimate of how likely a given test sample is to be from the training data distribution, right? So the model basically, without any labels, these models are being trained and they need to tell us how familiar am I with this test sample, right? So for that, we will estimate a quantity called sample likelihood, right? Because it's telling you how likely it is to be. So it's called sample likelihood. And what the model has to do is it has to produce a number, right? Typically a probability. So what looks like a probability, right? Which is high, that is, you have a high likelihood for what are called ID samples. ID meaning in distribution, right? So these are all samples that are familiar or well known to the model, right? In other words, these look very much like the training data, right? So a model that has been trained to look at dog images, for example, or cat images, when you show it a picture of a cat, it should say, yes, it's quite familiar. It may not have encountered that specific exemplar before, but it should assign a high likelihood to the image of any other, even a novel cat that it's being shown, right? Now, why is this useful? Now, with these kinds of high likelihood decisions, and if the sample has high likelihoods, then the model can make some kind of predictions or decisions confidently, right? because it knows it's quite familiar with that particular image, right? So then the model can make some kind of useful decision on it. But if it assigns low likelihood, right, and it should do that for out of distribution samples, that is samples that are unfamiliar, novel, right? Things that it feels it has never seen before. So for example, a network that is trained on cat images being shown an image of a truck, for example, right? It, in the case where the image is unfamiliar, the model should produce low likelihoods. And if it produces low likelihoods, we can say, well, maybe we shouldn't be making predictions or decisions about this input, right? Because I've never seen this input before. I've never been trained on this kind of input. So maybe I shouldn't be making predictions or decisions about this, right? So what we would like to do is in this unsupervised setting, when you don't have labels for the data, estimate something about the statistics, so estimate something about the likelihood of the test sample based on the statistics of the training data, right? So this is broadly the idea of outlier detection with unsupervised models. Is this idea clear to everyone? Any questions so far?
Yeah, it is clear,
No?
Professor.
Okay. So just as an aside, right? Why do we care about this type of unsupervised models? Many of the models you may have seen so far at this workshop, or even in your own work, or in the courses that you've done, are all supervised models, right? But as sort of aptly highlighted by Jan LeCun, Joshua Bengio, and Jeff Hinton in this review in Nature a few years ago, they said that we expect unsupervised learning to become far more important in the long term. Human and animal learning is largely unsupervised, right? We discover the structure of the world by observing it and not by being told the name of every object, right? This is, true for humans to some extent, but for animals almost certainly, right? There's like nobody, giving the animal labels about every object, right? It's sort of exploring and discovering the structure of the world. They can still do very sophisticated things without being given verbal labels about each object, right? So this kind of unsupervised learning is I would say a unique challenge. It has it's an unsupervised, this particular problem is still remains unsolved, this problem of unsupervised outlier detection. And today I'll give you some high level overview of how we are going to go about solving this problem. Okay, so I think this is a good time for me to do a mic check. Are you all able to hear me? Is everything good?
Yes, yes.
Okay, great. So, like I mentioned, please don't hesitate to stop and ask questions, right? Because it'll get a little bit hairy in terms of the, the math and all that in a few slides. Yeah. Okay. So then the question is, how do we measure sample likelihoods in an unsupervised setting? That is the question we're going to try to answer. Again, why do we want to measure likelihoods? If a particular test sample has a high likelihood under the model, right, under this particular model that we have, then presumably the model is more familiar with it, and then we can confidently make some judgments or classification decisions on it. If it has low likelihood, it's probably something the model has never seen before. Not necessarily, not only that exemplar, but just the general class of objects, right? Maybe it has never seen things like that before. So maybe you don't want for it to make judgments about that exemplar, right? So that's why we want to measure sample likelihoods. There are many different ways to measure sample likelihoods, again, in an unsupervised setting. And the particular model that we will be using is a model called variational autoencoders. Again, some of you may have encountered this model. It's a generative model, unsupervised learning model, introduced by Kingma and Welling in 2014. It looks very much like an autoencoder, for those of you who are familiar with autoencoders, but the philosophy, the principle of training are all a little bit different. Broadly, what it does, I won't get into too much details here. Broadly, what it does is it takes an input. This is your input image X, and it encodes it or compresses it into this latent space representation Z, right? This is a vector, right? So it basically compresses it into this latent space representation, right? So the Z is a compressed low dimensional representation of the input. And this network that compresses it or encodes it is called an encoder. Right? Hope you can all see my laser pointer. This is called the encoder. Now, there's another network here called the decoder. Incidentally, these networks can be standard MLPs, they can be convolutional networks, whatever you want, right? So there's another network called a decoder that takes this latent vector Z, right, and reconstructs the complete image from it, right? So you start with an image, compress it to a low dimensional representation, and then expand it again, decompress it to this, back to this original image space, right? This is the reconstructed image is X prime. Ideally, we want X and X prime to be the same, right? We want them to be identical, and that would be part of the BAE's loss or objective, as I'll show you in just a moment. But because this is a compressed representation, right? The dimensionality of X is usually, in this case, for example, this image is a 32 by 32 image with 3 channels of red, green, and blue, right? That's about 1,000, 10,000 pixels, right? Of, you know, not necessarily independent information, but you have that amount of information. And you want to compress it down to a low dimensional space, right? And what is the dimensionality of this space? It's typically about 100, right? It's on the order of 100, 30, 100, something like that. Right? Now, with this level of compression, it's not going to be easy to exactly reconstruct the image pixel for pixel. So typically VAE reconstructions look like this. What you're seeing on the right-hand side, hopefully, there's enough resolution in the monitor to show you this. So if you see, this is a very sharply defined image, but when you look at this reconstructed image, it looks a little bit blurry, right? The bird looks a little bit blurry, the flower looks a little bit blurry, and so on. And the reason for that is because you're doing this compression, right? You're compressing the image and then trying to reconstruct the image from this compressed representation. So you're unlikely to have all the relevant information, all the information that was there in the original image, but hopefully you have the most relevant information that will allow you to reconstruct essential aspects of the image, right? So even though this is a bit blurry, you can still recognize that this is a car, right? And you still recognize that this is like a flower, this is a bird, and so on and so forth, right? So there is this compression bottleneck in the VA. So you should keep that in mind. It's, encoding that image in some kind of very sort of an abstract feature space, yeah? Now, this looks very much like an autoencoder, right? So what is different about the VAE? One of the ways you can characterize that difference is that because the VAE is a probabilistic model, right? For every image or sample X that is presented, you can compute what's called the likelihood or the marginal likelihood. For those of you who are very particular about that usage, the marginal likelihood is called P of X, right? Again, I put some equations down here. I don't want you to get lost in these equations. But what was our purpose? We wanted to compute the likelihood for every sample, right? It's a sort of a measure of the familiarity of the network, right? So this is the equation that describes that P of X. Those of you who are familiar with Bayes' theorem, this looks very much like the Bayes' theorem, right? The Bayes' theorem, written in a slightly different way. Whereas typically we write the posterior as a product of the likelihood prior and then divided by the marginal likelihood, right? Whereas here you've written it the other way around. Here we've written the marginal likelihood as a product of the likelihood, the prior, and in the denominator, there's a term that looks like the likelihood. The true likelihood would be P of Z given X. But instead, we have this Q of Z given X, where Q is referred to as an approximate posterior, right? Now, why is it approximate? Because the VA is trying to infer something about this Q using this encoder network, right? There's a lot of theory and modeling work behind this. Again, I don't have time to go into this in too much detail because like learning about VAs, it's arguably like half a course in itself, right? It's a fairly elaborate topic. But I'll give you a high-level picture of what this likelihood contains, because if we're interested in this likelihoods, right? We want to compute these likelihoods for every image. So to help you understand that, this equation, right, whatever is there on the top, we've broken it down into two terms, right? This equation has become an inequality, And we've broken it down into two terms. Now the first part, this left term here, this log P of X given Z, is what we call the negative reconstruction error. This is a measure of how well the model can reconstruct its input. So it's basically a measure of the deviation between X and X prime. So the smaller the deviation between X and X prime, the smaller the reconstruction error, the larger the negative reconstruction error, right? P of X given Z. So P of X given Z is inversely related to the reconstruction error, right? So you want to maximize this term because you want to minimize the reconstruction error. You want to minimize the mismatch between X and X prime. Hopefully that's clear, right? This is one term. What's the other term? This term is a KL divergence between the approximate posterior and the prior. Now, what does this mean? Now, very simply put, note that this latent vector Z and its distribution, the approximate posterior Q phi, right, that generates Z given the image, that is generated by the encoder, right? So the encoder network is what is generating the Z, right? Which is, the parameters phi are all parameters of the encoder network, and they are basically compressing, the crunching X down to Z. Now, when you do that, you don't want a very complex kind of latent representation, right? You want as simple a latent representation as possible. And you can achieve that by penalizing the scale divergence between what the encoder is encoding and some kind of simple prior. Typically, these priors, again, for those of you who have a background in probability and statistics, these priors are typically taken as zero mean Gaussians with unit variance, right? So that's a very simple distribution, right? It's a sort of a spherical, very simple distribution. And what you want the network to learn, these parameters of the decoder and the parameters of the encoder, you want it to learn them so that in addition to minimizing the reconstruction error or maximizing the negative reconstruction error, you also want it to learn simple representations, right? And that's what this term penalizes. So if the network learns very complex representations in the latent space, it will penalize that, right? So that these representations that it learns are as close as possible. So the posterior is as close as possible to this simple prior, right? So there are these two terms. We want to keep the reconstructed image as close to the original image as possible, while not creating an overly complex latent vector, right? That's the two terms inside the likelihood. This is essentially what the VAE maximizes. This is the objective function of the VAE, right? So it's going to, as you present more and more and more training data, it's going to learn the parameters theta, which are all the weights of the decoder network, and the parameters phi, which are all the weights of the encoder network. And it's going to learn them so as to maximize this quantity. And it turns out that due to some mathematical jugglery here, maximizing this quantity is the same as maximizing the likelihood, right? So maximizing a lower bound on the likelihood, right? So once the network has learned after exposure to many such exemplars, we can then compute log p theta of x, which gives us the likelihood for a given exemplar. So now you present a new sample, freeze the network weights, and you ask it to produce this p theta of x. Again, the formula for computing that is on the right-hand side. You compute this p theta of x for that exemplar. These are the likelihoods of the VA for that sample, right? Okay, so if the math underlying this was not very clear, hopefully the intuition was clear, right, as to what the VA is trying to do, right? It's trying to learn a compressed low dimensional representation that's not overly complex, right? That's the idea. Okay, so now how can we use these VA likelihoods for outlier detection? And why should they be useful for outlier detection at all? Again, the math is a bit detailed, but I'll give you a high-level intuition for this. You can think of the VAE as a data compression network, right? Because that's what we said. It's a compressed low dimensional representation. So you can think of it as a data compression network. And keep in mind, there's only an intuition, right? There's a lot of gaps I'm leaving unfilled, but it's just an intuition. Because the latent representation has a bottleneck, right? The Z is much smaller in dimensionality than the X. Your latents have to encode characteristic features, right? Features that are most relevant for reconstructing the training samples. Why? Because you want to minimize the reconstruction error, right? Or maximize the negative reconstruction error. So unless you encode only the most characteristic features for that training set, you're not going to do a good job with reconstructing the training samples because you have a bottleneck in terms of the number of features in the latent space, right? Because the latent is low dimension. Okay, so for example, let's say I train a VAE with lots of images of cars, right? So there's like a bunch of images of cars. What the VAE will do at the end of training is come up with a latent representation that contains features of the cars, right? Something about headlights, something about wheels, something about like maybe the windshield, things like this, right? Now, with these features, it can very accurately reconstruct this image. And if you present an image of a new car that it has not seen before, it will be able to reconstruct it well because that new car that you show will have some features that are common to the cars that it has already seen, right? And so therefore, if it is an in-distribution sample, the VAE will assign that test sample high likelihoods because it can reconstruct it well. If it can reconstruct it well, it means the negative reconstruction error is high or the reconstruction error is low. But if the negative reconstruction error is high, the likelihood is high, right? So it's going to give you high likelihoods for samples that are easily reconstructed, right? In distribution samples. But now I take that car VAE and show it some dog images, right? I try to play some games with it. Then the VAE will have a lot of difficulty reconstructing these images, right? Because it has not seen this eyes, nose, ears, and things like this that are common to fur and things like this that are common to dogs, right? So because that feature space is extremely sparse and compressed, it's going to have it's not sparse. My apologies. It's a very compressed feature space. It's going to have a lot of difficulty with reconstructing dog-like images because it hasn't learned those features because it was shown mostly car-like features, right? So automatically what will happen is these will be more poorly reconstructed. Therefore, it will assign low likelihoods for them, right? Because the negative reconstruction error will be small, again, because the reconstruction error is large, and therefore likelihoods will also be small for these out of distribution samples. Okay, so this up to this point, let me just complete one assumption. So by looking at the likelihoods, I should be able to tell for a new sample, I should be able to tell whether that sample comes from a set of images that the VAE is already generally familiar with, like cars, or whether it comes from a sample that the VAE is not very familiar with, right? Like dogs. So I just need to look at the likelihoods and make that inference. And here there's an assumption, which is that these ID and OOD data have different characteristic features, right? Because if the OOD data also has features that look like cars and so on, then the VA will be able to reconstruct them very well. And so then you will again get high likelihoods for those. So there's an assumption here that the ID and OOD data have to have different characteristic features. Yeah. For this to work, for us to do outlier detection based on these likelihoods. Yeah. Okay, so any questions so far on this about things that I've said so far?
Dear participants, if you have doubt, you can raise your hand or else you can type in chat box.
Again, I'm not able to see what is typed, so somebody will have to read it out for me because I have.
Sure, sir.
I'm only able to see
Sure, sir.
So all clear so far. I mean, don't worry if you didn't follow the math, right? That will take some time to get familiar with, or maybe some of you are already familiar with it. But the broad idea is there. Yeah.
So like the assumption that you have mentioned here, like the in distribution and odd distribution have to be like having different characteristics. Sir, for example, like if we have some fake images that are quite similar to like the original ones, like then how these variational autoencoders like they obviously, I think, will work with little worse accuracy, I guess, if those are like some fake images of some like original image.
Yeah, so if you construct images that have car-like features in them, right, then this won't work very well, because the whole idea here is that the VAE has to, struggle to reconstruct those uh, images from the test sample that you present, and it will truly struggle only if that test sample has features that look very different from the training data. So if we construct fake samples that look sort of like the training data, it won't be able to detect them as outliers, right? But the broad idea here is, if you measure these likelihoods, you should be able to tell whether something was in distribution or out of distribution, as long as there is no feature overlap. That's an assumption, right? So that's a very clear assumption of this type of approach. If there is feature overlap, it won't work very well. Okay. So I mean, all of this hopefully convinces you that VAE likelihoods should work in theory, right? In theory, we should be able to measure these likelihoods and say whether a particular image is familiar to the model or not, right? But do they work in practice? It turns out they do not, right? And this has been sort of a major question in the field in the last couple of years. It's been sort of a major red flag about these generative models. So let me give you a very specific example here. So what we did here, again, this is some of our recent work, is we trained the VAE on this data set called Fashion Amnest. And for those of you who are not familiar with it, it has a bunch of thumbnail images with images of clothing, shoes, and so on. And then we trained that. That is the ID data, right? Those are the in-distribution samples. Then we presented MNIST images, right? So these are images of digits, like 6, 8, and so on, white digits in a black background. So we presented those images and then asked the VAE to give us likelihoods for every exemplar from the ID dataset and from the OOD dataset, right? Because this VAE was trained with Fashion Amnest, we expect in general higher likelihoods for Fashion Amnest images. That is the blue distribution here, as compared to MNIST, which is the orange distribution. But that's not what we see, right? We see the opposite. What we are seeing is the blue distribution, the Fashion Amnest ID samples are getting a lower likelihood than the MNIST, that is the OOD samples. Remember that these are samples that the VAE has never seen, right? Like it's never seen these numbers during its training. It's only seen articles of clothing like this. And yet it is assigning these samples higher likelihoods in orange here compared to these samples, the clothing samples, to which it should actually be assigning higher likelihoods, right? So you really want this blue distribution, which is the distribution of all the likelihoods across the test samples of the respective data set. You want the blue distribution to be to the right of this orange distribution, right? That's not what we see, right? Again, I'm plotting log likelihoods here rather than likelihoods, but because the log and there's a monotonic function, I'm not going to worry too much about log likelihood versus likelihood. Okay, so this same sort of problem arises even if you look at color data. For example, here we trained the VAE with celibae images. So these are images of with people's faces in them, and then tested on a data set with GTSRB images. So these are traffic signs, right? Speed indicators, stop, trucks, and so on, right? So it's going to have this kinds of images. And what we again should see is the blue distribution to the right of the orange distribution, right? So we should actually see celibae, because the VA was trained on celibae, we should get higher likelihoods for celibae images and lower likelihoods for GTSRB. But we don't see that. We see comparable likelihoods, right? These two distributions are completely overlapping, right? Heavily overlapping, right? So therefore, VAE likelihoods don't seem to work, right? It looks like if you train a VAE with some examples, with some training examples, and present another phase image to it, it will give it the same likelihood as if you presented another traffic sign, unrelated image to it, right? So what is going on here? It turns out that this is a pervasive problem with many models. VAEs are just one class of generative models. It turns out there's a very pervasive problem with many classes of generative models, like flows, autoregressive models like pixel CNN and so on. And there's a fair bit of work showing solutions for how to overcome this kind of problem with unreliable likelihoods, right? But it turns out that many of these solutions are very expensive, or they don't work with, many architectures. They don't work well in low sample regimes and so on. And some of these are particularly computationally expensive, right? They require training up like very complex models like pixel CNN over and over again for, over multiple kinds of data. So again, I won't get into the details of these models, but we'll be comparing our results with these models, which are all the state-of-the-art models, right? So, and the solutions that these models pose are all also fairly complex solutions, right? They're not simple ideas, right? They're fairly complex solutions for solving this problem. So what we did is to look at this problem with a little bit of a more careful eye. And we thought, is there something simple that we can identify as the source of this challenge, right? Why do VAE likelihoods not reflect the training data that they were shown, right? So even within the training data, right? So this is not ID and OOD data. This is ID data itself for the fashion MNIST VAE. I'm looking at all the exemplars in the fashion MNIST data set, which are getting high likelihoods and low likelihoods, right? Similarly, for the Celibae VAE, I'm looking at all the faces in the Celibae data set that are getting high likelihoods and low likelihoods. Is there anything obvious to you from looking at these images? Is there anything obvious about the likelihoods that you can tell just by looking at the images? Something very common across the two VAEs, right? Yeah, don't be shy. Go ahead and give me your best guess. So what do the images above look like? What the high likelihood images? Is there anything particularly interesting or unique about them compared to the low likelihood images?
Simple images giving high likelihood.
Sorry?
The simple images giving high likelihood.
I couldn't hear you. Sorry. Could you repeat? Simple images, certainly. One possibility is simple images, right? That this looks rather simple, correct? Anything else?
So
So you can see
background is very distinguishable from the foreground with the high.
Very distinguishable from the foreground, right? That is there. Also, the background is black in many cases, right? It is dark and black in many cases, right? So you have at least two things here. Keep in mind that the fashion MNIST VAE, most of the exemplars are not like these sandals, right? The high likelihood exemplars like these, like slippers or whatever here, those are not the most common images in fashion MNIST. The most common ones are like shirts, right? Like clothing, apparel. That's what is most common in the fashion MNIST data set, right? But what you end up seeing are these images, right? Similarly, in the Celibae VAE, what you end up seeing are these images having high likelihoods. And as you guys correctly pointed out, just by looking at this, you can see that the images with high likelihoods tend to have more black pixels, right? They tend to be, they tend to have like this black backgrounds and so on, dark hair, right? Things like this. And they also show stark contrast, right? Like somebody pointed out, it shows up very well, right? So this face is very clear in the black background, right? Whereas this face is not very clear, right? This person's hair, for example, and face are all more or less the same color, right? So it's very difficult to make out. So images with more black pixels are showing starker contrast, right? More obvious contrast tend to be assigned higher likelihood. And this was visible even by looking at these exemplars. So then what we can go in is quantify this, right? So what we can do is go in and quantify this. So if we plot either the negative reconstruction error or the log likelihood itself, right? And remember that the negative reconstruction error is a part of the log likelihood. So however NRE behaves, the log likelihood will also sort of behave like that, right? So this blue line here, which actually, unfortunately, you can't see because there are many lines here, but that blue line actually goes down and then up. And what is on the x-axis here? The x-axis here is just the pixel intensity of the images, right? So the image is very dark compared to when it's very light, compared to when it's somewhere in between, right? Grayish, right? So the dark images and the very white images tend to have high negative reconstruction error. And the intermediate images tend to have the lowest negative reconstruction error, right? So very dark and very light images tend to have high log likelihoods also as a result. So you have this U-shaped function, right? Now, when we feed this particular sort of image into a VAE, we get perfect reconstruction, right? Because for a VAE, reconstructing a patch of black or white is very easy, right? It just reconstructs it perfectly. But despite the perfect reconstruction, you see this very weird sort of shape in the negative reconstruction, right? This is the sort of the variation with pixel intensity. And we also see a similar variation with image contrast, right? So if you take an image and then you make it less and less and less sort of contrasting against the background, so you make it duller and duller and so on, what you actually see is again a drop in the negative reconstruction error and a corresponding drop in the log likelihood, right? So both of these things seem to decrease as the image contrast goes down, right? So you see a monotonic variation with image contrast. And keep in mind that this is happening even if the VAE is reconstructing the image, each of these images almost perfectly, right? So this is a bit confusing, right? Because the VAE yields different negative reconstruction errors, and as a consequence, different likelihoods, because again, remember the NRE is a part of that likelihood, right? It's a one term in the likelihood. So therefore, if the NRE is different, the likelihood also be different. But this happens even for perfectly reconstructed images, right? So what is going on here, right? Why should, by definition, a perfect reconstruction means the reconstruction error should be 0 and not different across images, right? And yet the VAE seems to, give different negative reconstruction errors even for perfectly reconstructed images, right? So it seems very puzzling. So what is happening here? It turns out that the devil is in the details, right? I'm not going to again get into the details again to avoid the devil here, but the point is that this whole negative reconstruction error bias, right? What you're seeing as a function of pixel intensity or contrast is a property of the so-called visible distribution that is used in computing P of X given Z, right? Because remember, we are not calculating negative reconstruction error like a pixel-wise mean squared error, right? We're using this particular function P of X given Z for computing the negative reconstruction error. And this function, the visible distribution used for computing this function, determines the bias. And in the images that I showed you before, this particular distribution that I used was called the continuous Bernoulli visible distribution. But it turns out that the bias also exists for various other classes of visible distributions that are used in standard VAE models. So how to correct for this, right? It turns out it's a property of the visible distribution. So how can we correct for it? Very simple. All you do is you take the NRE or the likelihood for perfect reconstruction and just subtract it, right? So imagine that the VA is doing a job of perfectly reconstructing the image, compute the likelihood, and just subtract it from the biased likelihood estimate to give you this corrected likelihood, right? This PCX is the corrected, bias corrected likelihood estimate. Very simple, just a subtraction, right? Now, how do you control for the contrast, the bias associated with the contrast? That also turns out to have a very simple correction. You just do a contrast stretching, a contrast normalization of the images as a pre-processing step, right? So as you can see, some of the images here, this image has low contrast. You can't see this guy's face very well, but this image has high contrast, right? You can see this person's face very well. But after contrast stretching, they all start to look similar in terms of how well you can see the face among the background, right? So there's a very particular way of doing this contrast stretching. And we've tried that as well as a few other approaches. And what we find is that after contrast stretching, when you compute the mean per channel variance across various data sets, images which were highly sort of heterogeneous in terms of their contrast distributions now become much more homogeneous, right? So all the images have more or less the same contrast. So we do this as a simple pre-process. It's just a pre-processing step. You don't have to do anything. You don't have to retrain the model, none of this. Just stretch the contrast. And in the previous correction, you just subtract this perfect likelihood post-hoc, right? So these both are post-hoc corrections. Now, what happens when you do the post-hoc correction? That is shown by the orange line here. And as you can see, there is no more U-shaped pattern. The negative reconstruction error and the likelihood also are all flat, right? As a function of pixel intensity. Similarly, as a function of contrast, right? So you've taken out the bias associated with the negative reconstruction error and the log likelihood. Bias associated with the intensity and contrast in the negative reconstruction error and in the log likelihood by doing these two corrections. Okay, so it looks like we solved the problem, at least in theory. Does it work in practice? It does. It does improve outlier detection very easily out of the box. And just to remind you of what I showed you before, for a VA trained with fashion MNIST, you want the blue distribution, that is the ID distribution, to the right of the orange distribution, right? But that was not what it was in the original case. But once you do the bias correction, that's exactly what you get. The blue distribution is to the right of the orange distribution, meaning that the ID data, the fashion MNIST samples, have a greater likelihood than the MNIST samples. So the VA is correctly telling us, hey, I'm familiar with these fashion MNIST samples. I'm not so familiar with the MNIST samples, right? So this is the correct direction of trends. And once you do the correction, you start seeing these correct trends. And for those of you who are familiar with this type of representation, this is called an AUROC, where you trade off the true positive rate with the false positive rate. And what we see is this kind of significant improvement. The orange is with the bias correction. We see a significant improvement in the AUROC following bias correction. Okay, so, and the same thing works for color scale data sets also. Again, this is a Celebi VAE. And before, if you remember, the two likelihood distributions are all highly overlapping. Now what happens is the blue distribution, the Celebi ID distribution, is to the right of the orange distribution, right? Not as clean as before, but definitely better than this case, right? So it's, the solution seems to be working, right? And if you now look at the exemplars with the highest likelihoods, you see much more meaningful and interpretable patterns, right? So for example, what do you see? The high bias corrected likelihood exemplars look more like standard articles of clothing, right? Like men's clothing, women's clothing, whatever it is, right? So you see this much more standard stereotyped exemplars. The low bias exemplars are complex things, right? Things that at a glance you may not even recognize as fashion apparel because it's got all these stripy things to it. It's got like, all kinds of, twists and turns and things like this that you don't normally see in apparel, right? Similarly, for Celebi, again, these faces, the more prototypical exemplars, look like normal faces in plain backgrounds. The atypical exemplars, right, the ones with the low bias corrected likelihoods, have all kinds of weird things around them, like this hat. Most of them seem to have a hat. This person, I think, maybe has some shades on his head. and this person has a light above his head, and so on and so forth, right? So you see these kinds of weirdnesses happening, these weird images being assigned low uh, bias corrected log likelihoods. And the model is telling us, hey, I don't think I'm very familiar with these, right? But I'm much more familiar with these, right? So that's what you would expect, and that's what you see, right? So the bias correction again seems to be working from this perspective also. To cut a long story short, we did this kind of analysis to check how the bias correction improves outlier detection with 4 grayscale and 5 natural image data sets. And also we also tested, noise, just, pixel noise, right? Uncorrelated noise as one more data set. And what we find is this is a 4x5 table, right? So you have 4 different data sets on which the VA is trained. Those are the columns, and 5 different data sets on which the VA is tested. These are all grayscale data sets. And in every case, again, you can look at the individual patterns in the paper, but on average, the blue circle are the standard log likelihoods. The orange squares are the bias corrected likelihoods, right? So this is the performance with the default standard log likelihoods, that is the blue circle. And the performance with the bias corrected one is the orange square. And you can see in almost every case, on average, it's improving significantly, right? So for the fashion and mist VAE, for example, it went from 66% to 99%, right? Similarly, for sign language VAE, it went from 31% to almost 100%. And these triangles symbols here are all the other approaches, right? And so we seem to be performing on par, if not better than state of the art. So the other approaches are these 4 clusters of 4 symbols that you see on the other side, right? But remember that these other approaches are fairly complex, right? They're very involved. They involve training up multiple models. They involve doing, a huge amount of optimization at evaluation time and things like this. Whereas this is a very simple correction. You just contrast stretch your image and subtract a quantity. That's it, right? Then you're done. And with just that, you're able to see this level of improvement in performance. And the same thing we see with natural image data as well. In many cases, we see fairly good improvements in performance. Like with the SVHN, for example, it goes from 50 to 93. Celibate goes from 73 to 90, and so on and so forth, right? There's an interesting case of the CIFAR VAE that, if time permits, I will discuss. I think I have about 5 more minutes, but if I have time, I will discuss it. Also to sort of conclude the sort of the sales pitch for this correction, it is also a lot faster, right? Because it's computationally inexpensive. It's very easy, just a subtraction, contrast stretching and a subtraction, right? It's almost 100% faster to evaluate than likelihood regret, which is one of the approaches that was doing quite well in the previous comparisons. So it's about 100x faster to evaluate. So this is the speed ups, and this is, if ours is 1x, this is 0.01x, right? So you can think of a likelihood regret being 100 times slower, right, than our approach. And unlike other state-of-the-art models like likelihood ratio, we don't need to train up multiple complex models and things like this. You just take your plain vanilla VAE and then do this correction, and you've got your outlier detection right there. Right? I don't want to get into this in too much detail given constraints on time, but it turns out that we can also do another kind of bias correction, which is again in the paper, called an algorithmic bias correction. And it works with many different categories of distributions, some of which are not amenable to theoretical analysis, right? So for that, we came up with a algorithmic correction, which is just sort of an empirical way to correct for these types of biases. So to summarize, essentially, what is the main portion of the talk? Bias correction and contrast stretching are very simple, they're effective, and they're also efficient remedies for outlier detection, right? Effective because perform on par with state of the art. Efficient because computationally inexpensive, you can do it very fast compared to previous approaches. Okay, any questions so far before I conclude with a couple of more slides? Can I also do a mic check and confirm that people are still able to hear me?
Dear participants, if you have questions, you can raise your hand.
No, so that's fine. We'll move on in the interest of time, but hopefully you understood the broad picture here, right? So what is the likelihood? How does the bias arise, and how do we correct for that bias, right? Okay, so the bias is again not a property of the model per se. It turns out to be something very artifactual with something called the visible distribution that we use for computing the the negative reconstruction error, right? When you reconstruct the image, right? So that artifactual bias is what we are subtracting and removing. And once we do that, the models, VAs seem to be working just fine for outlier detection, right? Now, I'll conclude with one sort of interesting failure case. So if you notice this for the CIFAR-10 data set, right? So we have this CIFAR-10 data with these many different categories of images, right? It has airplanes, it has cars, it has birds, cats, and so on. For that data set, this bias correction didn't help very much. So this blue color circle again is the performance with the original likelihood. It was about 50%. But with the correction, it didn't go up to like 80%, 90%, 100%, and so on. It stayed at 60%, right? It didn't help very much. And so we asked ourselves, what is going on here, right? Why in CIFAR 10 is this correction not working? To answer this question, I would like to remind you of the assumption we made in the beginning, right? We said that the ID and OOD data must have different characteristic features, right? They must not be overlapping in terms of features. But then we asked ourselves, what are the characteristics features of CIFAR 10, right? Because there are so many different kinds of images in this, it's, I can't define eyes, ears, or anything like that as a characteristic feature of CIFAR 10, because that is there for the dog images, maybe for the cat images, maybe for the birds, but definitely not for ships and trucks, right? And so it becomes very difficult to define what are these characteristic features for CIFAR 10 images, right? So in that sense, these images aren't great in terms of having those types of characteristic features. So in some sense, it's not particularly surprising that this approach didn't work. So what can we do to rescue it? Now, presumably, every category of CIFAR 10 images would have characteristic features, right? For example, it would have characteristic features like wings, like tail, on. Deer would have characteristic features like these antlers, face, and so on. Similarly, frogs, similarly, ships, and so on, right? So each subcategory within CIFAR would have its own set of characteristic features. So what we did is we said, let's train different VAEs for the different categories of images. Don't put everything in one box and train it as CIFAR 10, but put them in different boxes and train different VAEs for each different category. And each presumably has some unique characteristic features. Does outlier detection improve with VAEs if we do this? Turns out the answer is yes. So if you actually now take only the ship data, for example, and look at outlier detection against two other like Celebi and GTSRB data sets, this VAE was trained only on the ship category of CIFAR 10 images. You see a huge improvement in the outlier detection performance, right? So it goes from by about 60 points, there's an improvement by 50 to 60 points there, right? Similarly for the other categories also, right? So if you then look at individual categories of images, the VAE seems to do very well, right? So suggesting that the failure in the CIFAR 10 case is not the failure of VAEs or of our solution. It's something specific about the data set, right? About the heterogeneity of that data set. Okay, so let me summarize the talk. So we started out by defining outlier detection, why it's important, why it's an important question, because we want models to know what data are familiar and what are unfamiliar so that they can avoid incorrect or overconfident predictions, especially with unfamiliar data, right? You don't want the model making decisions based on that. So you need to say, okay, this is an outlier. I don't want to make decisions about this. Specifically, we discussed unsupervised outlier detection, which is a major challenge when you don't have labels in the data. The model simply has to learn something about the statistics of the training data and figure out whether the test data is an outlier or not. So it's a major key challenge. And in my view, it still remains an unsolved challenge, right? There are There are some solutions, but not all of them work in all cases. Now, these VAE likelihoods are a candidate for outlier detection, like we saw. These likelihoods can be used as a measure for whether something is an outlier or not, but they were heavily biased by low-level statistics, right? Like intensity, contrast, number of black pixels, how well it stands out, and all of that. Then we propose some very simple solutions. Bias correction is basically a subtraction, right? And contrast stretching, which just means, contrast normalization, right? What you would do in your monitor for, making things stand out much more. Quite effective. To give you performance numbers comparable to state of the art. Also computationally inexpensive, right? Very simple solutions. And what we are exploring now is whether these types of solutions can be applied to other classes of generative models like pixel CNNs. Right? So again, some of you may have heard of these like autoregressive models, which are much more complex models, more difficult to deal with and handle. So we're checking if some of the solutions that we have proposed here are also applicable to those classes of models. So with that, I'd like to finish and give a shameless plug to our lab, the Cognition, Computation, and Behavior Lab at CNS and CSA at ISC. Among our many goals is to leverage AI for understanding the brain and to develop brain-inspired AI models as well. So we sort of go both ways. We straddle both ends. I'm both a neuroscientist by training and also a computer scientist by passion. So so we're sort of straddling both ends of that interesting brain and AI interface. And I'll finish by acknowledging the students in the lab, collaborators other than the Google collaborators who I showed in the previous slide, as well as the funding agencies that made all this work possible. In particular, Google Research India, which has been very generous with supporting all of the work shown in this presentation. Thank you, and I'll take some questions now.
Dear participants, if you have doubts, you can raise your hand.
Good afternoon, sir. I have a doubt. According to your opinion, whether this variational autoencoders, what would be its result on medical images like X-rays, MRI images? Will that work good? Like the distribution might appear the same, like since it has the same background like X-rays and MRIs. So, what is your opinion, sir?
So that's a great question, and actually, it's a direction that we are also moving in terms of because so far we've looked at these standard computer vision data sets like CIFAR, SVH, things like this. But we are also very interested in understanding whether this can be used in medical imaging applications. Because what is an outlier in medical imaging applications, right? So if I present the VAE with, for example, X-rays or brain scans of thousands of normal participants, thousands of normal individuals, and then I presented test samples from somebody who has brain pathology, right, or some pathology in the X-ray, right? Will the VAE be able to tell whether that scan or that person is abnormal, right? So that is a key application of these VAEs, right? So you can actually use these VAEs for detecting outliers based on pathologies that show clear deviation from the norm. Now, whether they will suffer from the same biases that I showed in this presentation, almost certainly, right? Definitely. So we want to use these solutions in that context also, and then see if our performance on those data sets improves even further. But because those are very specialized data, right? Unlike these images and all this, those are acquired in very stereotyped and specialized settings. We may need even more interesting ideas to improve outlier detection for those data sets. Because those are very specialized kinds of images, right? So we may need some both specialized knowledge and more particular solutions to make VAEs work in that setting. But that's what we are exploring now. So that's a very relevant question. Thank you.
Thank you, sir.
So any other questions or thoughts about the presentation or the
Hello, good afternoon, sir.
Yeah.
Yeah. Like in connection with the question which Devika asked, so I have a similar kind of question. Like, if suppose in medical field we are using multi-modalities as an input, so in that case also this model will give similar kind of results when it is applied for single modality. Or is there any, because there, as we are using multiple modalities, so we try to get more and more different kind of features from that. So there also this kind of thing will give us the better results.
Yes. So so that's a great question. So the question is, for example, can we combine sort of different modalities of images and maybe other kinds of information about the participants, maybe genetic information, many other types of information are there. So in that multimodal setting, there are slightly more sophisticated models that can be used than plain vanilla VAEs. So those are models where, in addition to these VAEs, these additional information like genetic information and so on can be used for something called conditional generation. So where the VAE, the outputs depend not just on the sort of the image that was shown, but it also depends on the image that was shown, as in the scan, for example. But it also depends on the genetic profile of the participant, or the blood profile of the participant, or something like that, right? So, or maybe you have two different modalities of images and you want to fuse them together. So in that case, again, there are certain semi-supervised VAE models that can be used in that setting, conditional VAE models and so on. And so that's also in a direction that we're very interested in exploring. But to sort of give a short answer to that question, in all of those types of models, we expect these biases to be present. And those biases are going to definitely affect the output and the accuracy and the confidence and so on, unless you're very careful to control for them. So that's, I would say, definitely a take-home message from this. The generative models in general seem very susceptible to these types of low-level biases.
Yeah, thank you so much, sir, and thank you for the wonderful session. Thank you.
Sure. Yeah. Thank you.
Thank you very much, sir.